Time for isomers. So we've talked about isomers before. When you have the same formula but different connectivity, or they could be optical isomers when you have chiral things. And we are also going to talk about those in regards to coordination chemistry. So in coordination compounds, so all of these metal complex things, again, isomers are things that have the same structural formula. They can either be put together or connected differently. So atoms in a different order, like they're bonded differently. Or they could be stereoisomers, which has to do with their 3D spatial arrangement. Okay, so different bonding or different spatial arrangement. It still applies. So I'm first going to talk about structural isomers, ones that are actually connected differently. That's a regular typical isomer. So there are two types. There are coordination sphere isomers and linkage isomers. A coordination sphere isomer is when the ligands actually bond, the ones that were bonded trade places or exchange with ligands that were outside of the coordination sphere. So for example, if I have this compound, this is a purple compound, chromium with 6 waters on it, and then not attached to it are 3 chlorides. If they switch places in any way, so this compound, I only have 3 waters and 3 chlorides on the inside and 3 waters on the outside. So now it's the same formula, but it swapped 3 waters for 3 chlorines. This would be a coordination sphere isomer, and they are actually different colors. So depending on how they're bonded, you're going to get those different colors. Okay, a linkage isomer, on the other hand, is when the ligands bond with a different atom. So for example, NO2 minus, so this nitrite ion does that. You can either bond to an oxygen or you can bond to a nitrogen, and you get different colors based on those. So for example, this has 5 nitrites on it, nitrates, these ones are nitrates. This one's bonded at the blue, which is the nitrogen. This one, oh, sorry, and O2 down here. That's what I was talking about, the nitrite ion. So this one down here is bonded at the blue, this is the nitrogen, and this one over here is bonded at the red, which is the oxygen. So depending on where that ligand is bonded, it's the same molecule that's bonded, it's just a different atom that's bonded to it. You actually get different properties. Okay, so coordination sphere is swapping, and linkage is attaching a different atom from the ligand. Okay, now stereoisomers are connected the same way, but in a different 3D orientation. Okay, so again, we have different types of this. There's geometric isomers, and then there's optical isomers. So geometric isomers are the one we're probably going to spend the most time on. So these have different orientations. Okay, we can have 2 types of geometric isomers. There can be cis-trans and FAC-MER. Okay, cis-trans are the easiest ones to figure out. So cis-trans ones only come about if you have something that is square planar or octahedral. So these are the only times that you can have a cis-trans isomer. Because if you look at the square planars, you can either have, like if I've got different things on here, right? I have 2 chlorines and 2 ammonias. They can be on the same side or they can be on opposite sides. Okay, so this one is cis and this one is trans. You can also do that if you have an octahedral compound that has 4 of one thing and 2 of another, because you can, if you draw it this way, you can have 2 of the chlorines right next to each other, or those 2 chlorines opposite each other. Okay, so these are different arrangements. So cis-trans can only happen for square planar that has 2 and 2, or octahedral that has like 4 and 2 of their different groups. Okay. FAC-MER only happens if you have octahedral that has 3 of one thing and 3 of another thing. And the difference is FAC stands for facial, meaning one face, and MER stands for meridian, or the middle. And so if you look at these complexes in 3 dimensions, I've got 3 ammonias and 3 chlorines, right? So if you were to connect all of the chlorines, they are all on the same face. So that's FAC. And if you, in this case, were to look at the chlorines, they are all in the same plane. So they're all down the middle. This one is called MER because they do not connect and make a face. Now, how do you draw these in 3 dimensions? This is how we draw octahedral compounds, because you are going to have to do this. Put the metal in the middle, always put 1 up and 1 down. And then you do 2 wedges and 2 dashed lines, or dashed wedges, however you want to draw it. The wedges like this, or the filled in wedges, mean they are coming out of the paper at you. And the ones going into the paper are like ones going in. So it's like you have the up and down in a line, and then you have 2 going out and 2 going back because they're in 90-degree angles. So this is how we're going to draw them so that you can easily show me square planar. Well, square planar is flat, so you don't have to draw that in 3 dimensions, but an octahedral cis-trans or an octahedral FACMER. There are also optical isomers, so the non-superimposable mirror images when things are chiral. This is only possible for a 6 coordinate, so an octahedral complex that has 2 or 3 bidentate ligands. Okay, this is an example. I am not going to make you draw these because these are very difficult to draw and differentiate. Okay, so if it has an optical isomer, I'm not going to make you draw it. All right, so example number 9 has you decide whether or not the complex can exhibit cis-trans or FACMER isomerism. Some of them can't. Which of these can have optical isomers? And I wanted you to show sketches. I don't want you to show sketches if there's just an optical isomer, but if there is a cis-trans or a FACMER, I do want you to draw them. So you can try that now if you want to, or I will talk through all of them. Okay, so in part A, cadmium has 2 ammonias and 2 bromates. Now that has, it has 4 things bonded to it, but since I told you it was tetrahedral, there's no isomerism present. We don't have, if you're looking at your options, any way to differentiate if they are tetrahedral, only if you have 4 bonds and it's square planar. So this one has no isomers. This one, though, has 2 bromines and 2 chlorines, and it is square planar. So that means it can either be cis or trans. So cis would mean they're drawn on the same side, or trans would mean they're opposite sides. So you can draw this one flat, does not have to be 3 dimensions because it is planar. Okay, this cobalt one, however, down here, I've got 3 and 3. So I have octahedral. And if you have an octahedral complex, it can be FACMER if you have 3 and 3. So the way that I draw this is I put my thing in the middle, and then I choose which ones I'm going to use to figure out my FACMER. So I chose chlorine, and draw your up, down, and then your in and out of your paper angles. Okay. Now, if you put them both on the same wedges or dashes and up, so group them together, that's a FAC. And if you put them all along the middle, chlorine coming out at me, chlorine going down, that's MER. And you can probably see it from the waterway as well. But that's how I figured those 2 out. So draw the bonds and then stick the stuff on. Now over here, I have a 4 and 2, so that's not a FACMER octahedral. That can be a cis-trans octahedral. So again, draw all your bonds and then stick your stuff on there. So it's really focus on the chlorines. I can either have the chlorines opposite each other, which is trans, or next to each other, which is cis. So your drawings might not look exactly like mine. Look, I can. And then in part E, I have this one, which has this guy. This is 2 bidentate ligands, and it also has 2 waters, but that means it can have an optical isomer. So anytime you have 2 or 3 bidentate ligands, you can have optical isomer. So I won't make you draw that, however.